So welcome back. I wanted to say a few words because there were a few questions during the break on the quizzes that give you bonus points for the exam. So here's how it works. So technically, you have roughly 1 week to solve them. So they are released, I think, Tuesday at noon, right? So you have until next week, also Tuesday at noon, to submit your answers. By default, you have one attempt allowed, and you can click on submit when you're done, and then that submits your attempt. You can also start preparing answers, but not actually submit the attempt and just wait and think about it during the week. This is fine too. Now, what happens if you submit an attempt and then you realize 2 days later that you would like to change an answer because maybe you change your mind? When it's possible, then just send an email to the TA team and ask for another attempt. We will then gladly grant you another attempt, and you can start again and put another answer. Of course, we take the latest attempt as your solution. Now, you might be wondering, why do we do this? Because we actually tried to just allow for unlimited attempts, and then we realized there was a flaw in the system that you could do a brute force attack by just submitting answers with all possible combinations until you pass. And of course, that's not exactly the spirit of the bonus points, right? So this is why we changed it to this way, but really do not hesitate and ask us. It's totally fine to change your answers and give another attempt before the final deadline. Of course, avoid asking 10 minutes before the deadline because that's not very easy, but if it's sufficiently asked in advance, then it increases the chances we actually read your message. That was it, right? Martin, there was no, yeah, all right. So now I'm going to continue. I asked you what data centers look like. There is this saying that actually we hear a lot on the quantum side, which is that information is physical. I usually like the other way around, that physics is informational, but somehow here reality calls us back and reminds us that the data that we are dealing with, even though we have data independence and the beautiful world of thinking in terms of tables, in the end, all of that must land as bits somewhere on a storage media. We don't have a choice about that. It has to be somewhere. So this is why we have the database, that's the data itself, but physically it's actually stored somewhere. And that somewhere, as you might guess, is eventually going to be some sort of drive, right? Either a mechanical drive or a flash drive, but it's going to be something looking like that. So how do we do this typically in databases? This here is extremely important. I'm going to give you a distinction. It's just as important, you know, as denormalization, materialization, all of these concepts we'll see throughout the course. We have two ways of dealing and interacting with data. And both of them are okay. You need to just realize depending on your use case. The one on the left is when you have a database management system like PostgreSQL, IBM, Oracle, and so on, that kind of takes care of everything, right? It's this huge black box, then you can connect to it with SQL, with interface, and so on and so on. And then there are ways to import your data and store it in there. It's called extract, transform, load, or ETL. ETL is even a verb. So you ETL your data into the traditional database, and then you can query it using SQL or any other language. Why? Because since you use the interface to add the data to this database and it imports it, the system can decide itself how it stores the data. The way it's stored on disk is entirely the decision of the system. And as you can imagine, the systems are going to optimize things. They are going to store it on disk in a way that will make your queries fast. So they are highly optimized. That's the benefit you get. The cost to pay is that you need to import your data. It takes a while to do. But once you have done that, you have queries that are really, really fast. And then you have data lakes, which is a different paradigm. The idea of a data lake is that you just dump your data onto some low-level layer. It can be a file system, can be, as we see, cloud storage, and so on. You dump your data. It's going to be as files. For example, an XML files, JSON files, CSV. There are all kinds of formats. We'll see Parquet also. So you dump your data there, and then you query it using some technologies, right? Some of the popular ones that are discussed and they actually work is Python with pandas, right? So you read your data from the disk using the pandas library, and then you can access the data, right? We'll see others, of course, that work at very large scales, which is MapReduce, Spark, and so on. And on top of that, we'll even throw in RumbleDB, but there are plenty of ways that you can query your data on top of a data lake. There are pros and cons. There is no one, this is something general that I keep telling, especially for computer science data students. There is never, ever a single technology that is the answer to everything. That doesn't exist. You always have a use case, and for that use case, you have to pick the best technology depending on that use case. And it might be that for some use cases, this is the way to go with a fully integrated database management system. For other use cases, then a data lake would be the way to go. It's the same thing there are plenty of examples of that, but the debates like, should I use XML, should I use JSON, and all the debates that it triggers on the internet, which is actually fun to watch. But really, the one thing that I want you to keep in mind is do not be stuck on a single piece of technology or in a single paradigm. This is not how a computer scientist should do it. You should really be open to plenty of technology, like a toolbox available. And for every one of the problems or use cases you want to solve, then you are able, with the knowledge that you get in this course and other courses, to pick the best technologies in order to solve your problem. Right? And of course, to do that, you need to understand what's behind and inside the technologies, right? So this is why we're going to spend a lot of time looking inside. So we have the traditional database paradigm, and we have the data lake paradigm, right? Be careful. If you use the data lake paradigm, if you don't pay attention, you can end up with a huge mess. Like you have a system, and then you have all your data that you don't even know what it looks like, or you can really lose the overview. So really be careful with data lakes. And also, it's much harder to get good performance out of a data lake than a traditional database, because the traditional database will take care of it for you. The data lake, you're kind of on your own, right? So you need to be a bit more experienced to use it. Today, we are going to look on the side of the data lakes, because we are going to look at cloud storage, which is one of the ways, one of the storage media that you can use for a data lake. All right, but back then, data lakes didn't really exist. And so we stored things on disks, even though you could consider the disk as a mini data lake, right? In a way, what people were doing in the 60s is that they were using the disks as mini data lakes before the database management systems were invented. So we had the disks. And so back in the 60s, the files were stored like this in this mini data lake as a hierarchy of files and directories, and then they would write programs that access the files. Now, you might know, most of you, from bachelor's lectures on computer architecture, that on these hard drives, like this, so the files are actually stored as blocks. I'm not sure why this is stopping working. Maybe the batteries are running out. So the files here are stored as blocks on this, right? And the size of a block is roughly, is it megabytes? Kilobytes, exactly. It's more like something like 4 kilobytes, 8 kilobytes, 16 kilobytes, maybe 32 kilobytes. It really depends on the format you use, right? But it's stored in blocks. Why blocks? When we'll see, it has to do with the throughput and latency thing. Is if we didn't have blocks, we would wait forever until, if we get the bits one by one, you will still be there next year to read your file. But since it's stored in blocks and we read one block at a time, it actually avoids the latency. And I'll talk again about this next week. So maybe there could be a chance that we build our cloud storage system by just taking a drive like this, and we connect it to the network. Maybe some of you have this at home, and you connect the drive to the network, and then you access it from anywhere, right? With a LAN, with network attached storage. I put all the terminology abbreviations right there. LAN is the local area network. The problem is that it doesn't scale, right? You will be able to connect it to the internet, maybe for you, for your family, but as soon as you want more people to use it, that just doesn't work. There is also a problem with the number of files. Maybe some of you know the order of magnitudes of the number of files on your disk because of backups. Who does backups? Who doesn't do backups? Who already lost their files? Okay, you should really do a backup, right? But if you do a backup, you probably will get an idea of the number of files you have. And that number might be somewhere between 1,000 and 1,000,000 files, but certainly not into the billions, right? And this is where we have a problem, because one of the use cases that led to cloud storage is companies like social media companies that need to store a huge number of pictures, right? Or a huge number of videos, like even streaming, like Netflix, Disney Plus, and I have to cite several brands just to make sure I don't advertise for anyone over another, but basically they use these systems. And you need billions of files in this system. So you can clearly not do it by just attaching a drive to a network. That's not how it works. However, if we come back to this analogy that we had, if we assemble plenty of drives in a way connected to the network with plenty of machines, then that actually might work. So if we want to build a cloud storage system, what we can do is, as a common way to scale, we simplify everything. So we throw away the hierarchy. No directories, no files, it's just key value, right? We are going to see. So we throw away the hierarchy, we make the data model trivial, and we end up with something like this that is just a key value model, and we'll see key value models all over the place in this course, where we just have a global namespace where keys are associated with values. So a key is just the name of an object, and the value is the object. It can be 10 seconds of a Netflix series, or it can be an image, or it can be a data set, and so on, right? But it's global, right? So this key is worldwide, and if you give me a key, I can give you the value that's associated with it, or I can store a specific value associated with a key. Now you probably already noticed a shift of terminology, because I didn't say file, I said objects. And in fact, object is the name that we give to the files in this terminology. And we in fact call it object storage. So there are plenty of technologies that do this, right? So this is the logical thing, right? And again, I can have billions and billions and billions of objects in there, right? That I store, billions of keys, billions of values.
We have a question.
Yes? Yep, almost.
Thanks. So the question is this abstraction after the file system level, or is it below it, or are we implementing that file system of our own?
Sorry, can you repeat, please?
Is this abstraction below or after the file system level? So you were saying we're not calling these files, but objects, because, well, files is what the file system has.
So the answer is it depends.
Okay.
Today, it's actually below, in the sense that I will show you how you can actually put or simulate a file system on top of that. But there are other examples where it's above, that you can implement some key value model on top. So here it's really about, you know, what we are going to see in that course is really just a big set of components that you can assemble in plenty of different ways to make it all work. So even when I said data independence, there is a physical layer and there is a logical layer. Sounds simple, right? But in practice, you're not going to have 2 layers. You might have 50 layers, right? And depending on where you are, seen from here, this is logical, and seen from there, it's physical, right? So for example, when we talk in my research group with people dealing with FPGAs, and they talk about like the physical implementation of the FPGAs, and something like, I don't know, reading the cache is logical compared with the FPGA. I'm telling them, I'm a database person. For me, this is physical. Like anything that's below, you know, querying the data and so on, that's physical. So it's all a matter of perspective, right? The way you assemble this. And this is for this reason that I'm saying, depending on the architecture, depending on how you assemble the components, you have cases where this might be some layer in your system below the file, the exposure of the file namespace, of the file hierarchy, or it can be above. right? But the key part, when we design these things, and this is what computer scientists do, you abstract from the environment. So whenever you deal with this, you kind of ignore what's above, you ignore what's below. Some people call it north and south, the two directions. But basically, you assume some way of interacting with whatever's more physical and of interacting with whatever's more logical, right? Did I address your question?
Yep, thanks.
Yeah? All right, and I'll come back to this, of course. I'll show you when we come to actually integrating that with the file namespace. But right now, forget about the file hierarchy. Forget about it, just key values and that's it, right? Keys and values. Okay. So we need to make it work because, of course, it's easier said than done, right? I told you we have billions of key values. Logically, it's easy. Physically, how do we actually do that? Well, generally, what can we do? Let's say I have my laptop right here. It has some memory, it has a few cores and so on, and it's too slow or things don't fit on top. So what can I do? Well, the first thing that I could do is buy a bigger laptop. Maybe I can buy one with 64 gigabytes of memory and 32 cores and maybe 2 terabytes of disk, right? Or 4 terabytes of disk. So I can just do something that's called scaling up. I just buy a bigger machine. But there's a problem with that. There's a problem with that is that it's not linear. Of course, if I double my memory and my space on the drive, I might think that's twice the cost, but no, look at the catalog. It's not twice the cost. It might be 4 times, 8 times the cost to actually do this. And if you want to build a computer, I'm taking now a caricature, of course, but imagine that you want to build a computer with, I don't know, 100 terabytes of RAM, of working memory, and 100 terabytes of disk, and 1,000 cores of CPU. How much is it going to cost you? Well, you can do it if you're a billionaire. And you might spend like tens or hundreds of billions of francs in order to do this. And maybe sometime around 2032, you're going to have this. But it costs you a fortune, and it took time to do it. So this obviously doesn't work all the way. You cannot just scale up and buy a big computer and hope that it's going to do the trick. This is why we do something else in practice that's called scaling out. Scaling out means we don't buy a larger computer. We just buy more computers, small ones, but more of them, plenty of them, thousands of them. Right. And this is called scaling out. So remember this terminology: scaling up, scaling down. It means you make the machines bigger or smaller, scaling up and down. Scaling out, you increase the number of machines, and scaling in means you reduce the number of machines. Up, down, in, out, the 4 adverbs that you can use. All right. And so the idea is really this: scaling up is not linear. It's more like exponential. In fact, it's almost hyperbolic if you really want to consider that there's hitting a wall at some point. But scaling out is just linear. At least it's linear for a while. You know that everything has a limit, right? If you want trillions of computers, you obviously will run into supply issues. But at least for the scale that we're interested in, for a while, it's just linear, right? So this is why we like to scale out rather than scaling up. Now, there is a third way. That's my favorite way. My favorite way is to think and write better code. Because very often, the reason why it's slow is that you didn't go all the way to writing good code. You might have improved the performance by changing a bit your code. You could also use less space by compressing your data. And there is a concrete example we'll see in a few weeks. But if your data is stored in JSON, that takes a lot of space, right? But what if your data set has a schema? It's always the same keys, it's always the same types. Then there are more efficient formats than JSON to store the same data set. We learn how to do this, to convert between formats and so on. But basically, you should try to think about these things, right? The space that your data takes and the code that you use. And of course, having query languages and so on is part of the way you can actually increase your performance, because you outsource to other people, specialists, writing the actual implementation. But this is very important. And in fact, this is a quote that I really like. You will have a second computer once you've shown you can use the first one. So I cannot emphasize enough how important this is. And in fact, that's probably why in this course, we're going to use your laptop a lot in a Docker environment, right? You really need to make it work on a single machine. This is also a very, very important tip to people who found startups. Many people make the mistake of starting with a cluster, but for the wrong reasons. Because in many cases, the data set that you use is actually not that big. It fits on a single machine. You can make it fit on a single machine, and you can write code that will run on a single machine. In many cases, actually, it works. You need to use a cluster if you know what you're doing, if you have reasons to use the cluster. For a startup, one reason to use a cluster and be in the cloud is the ability to quickly expand if suddenly you have a lot of users. This is one of the ways, the elasticity of the cloud. But you really need to think about these things. Do not rush into booking machines on a cluster. Think about what you're doing, the quantity of data. Can you compress it? Can you store it more efficiently and write code? Once you've done that, then you can start scaling out. Actually, it's very exciting to try to make your code better, like squeezing as much as you can from your laptop. And I hope in this course, you see how much you can actually squeeze from your laptop and all the cores. It's very impressive. So we scale out. So you see, you can also do big data on your laptop. You don't need a cluster. Okay, so scaling out is what we will use. I think that this is getting on strike. Doesn't want to, yeah, I might consider to change the batteries at some point. All right, which brings us to data centers. So I'm a database person. It means that hardware is all the way down. It's really a physical layer down there. But I have some sort of abstraction of what hardware is when I speak with my colleagues, right? So I know that there are CPUs. That is how you compute stuff, right? You have the registers and the instructions, the von Neumann architecture. And I'm giving you orders of magnitudes, but technically on a single machine, you have somewhere between 1 and 200 cores. It's just an order of magnitude, right? This is on a single machine. The number of machines in one data center, it's typically between 1 and 100,000. 1,000 and 100,000. 100,000 is really an upper limit. I don't think it's known today if any company managed to actually break past the 100,000. There is actually a reason why it's very, very tough, is that a data center consumes a lot of energy. In fact, we had a field trip a few years ago into a data center on the north of Zurich. There is something called the fiber optics highway around the city. It's not in the mountains. I mean, a lot of people think it's all in the bunkers under the Alps, but actually right here in Zurich, there's a lot of data centers. And I think they explain a data center consumes as much energy as the airport of Zurich. This is the energy that it actually takes in terms of electricity. And of course, when you consume energy, that actually generates a lot of heat, right? It's just the second principle of thermodynamics, right? So a lot of heat. And you have to cool that down. So you need cooling for this. You can do it with air, with water, with some specific fluids and so on. But it's hard to do. And once you have 100,000 machines concentrated at the same location, you're hitting the limits of that, right? It's very tough to get better than that. So what you do is just you build other data centers at other places, but it's very tough to go beyond that limit in the same data center. All right. We don't have all the numbers because some of that is actually not open data. So we don't know the exact numbers. It might well be that by now some companies actually are above that, but it's tough. Now on the same machine, you might have between 1 and 30 terabytes. It's an order of magnitude. It might actually be more than that if you really plug a lot of different disks on the same machine. Here, I'm talking about the single disk, right? Then, of course, there's ways that you can assemble arrays of disks and get more. The limit here of having many disks in a machine is really how fast can you read, as we will see, right? So this is the motivation for spreading the disk across several machines. Then we have the working memory. which is when you actually process the data, it's not directly from the disk. You load it into memory and manipulate it in memory. So the RAM, random access memory. And here it's somewhere between 16 gigabytes and 6 terabytes, right? It keeps increasing, of course, but these are the orders of magnitudes today. The bandwidth also keeps increasing. By now, it's between 1 and 100 gigabit per second. When you talk about the network, typically you talk in bits and not in bytes, right? You just need to remember that there's a factor of 8 between bit and byte. So typically at the level of a network, you really look at individual bits because of information theory, but between 1 and 100 gigabits per second. How is this all put together? Well, it's not like you put plenty of desks in the data center and put laptops on the desk. That's not what it looks like. Instead, you pile the machine on top of each other. This is called a rack, R-A-C-K. So the machines are here, stacked like this. And there is this standard unit called the rack unit, 42 rack units, which is just a standardization of the manufacturing of these servers here. There is a name for these, we call them nodes. So I might use the word server, node, machine interchangeably, right? So these are called nodes. What can you have in this rack? Well, you can have these nodes, these servers. You can also have pure storage nodes, meaning that all you have is disks in some of the layers. You can also have routers, network switches, and so on, which you can also assemble in there. So typically you have a lot of machines, then you might have some disks on some floor, and then a network switch somewhere to connect it to the rest of the data center. Okay, but it's all modular in this way. So this is a zoom over what it looks like. So between 1 and 4 rack units is basically the height of this, and then you have a server, and inside it's pretty much the same components as you have on a laptop or a desktop computer, except that it's flat. It's just organized in this way, right? All right, so this breaks the myth of what there is in a data center. Now you know what there is. It's plenty of these things next to each other. Now, the data center, it's the physical location. And on top of this, there are providers of resources. I think it shouldn't surprise you that I'm going to talk about Amazon in this context. It actually did surprise in the other version of the lecture, big data for engineers, not computer scientists. Like, why are you talking about a bookseller in a database lecture, right? But there is a reason for that, and actually it's one of the main businesses now of Amazon. They had trouble. I think it was in the holiday season of 2004. That was already something like 19 years ago. Because guess what? Everybody wants to buy their gifts at the same time. Can depend on the country, of course, but there is a tendency for the gifts to be concentrated in the same period. And of course, when that happens, then you might not have enough nodes or enough servers to basically make sure that everybody can order. Of course, that's a big deal because you make money out of selling books, right? So you want people to be able to place their orders. So what do you do when you buy more servers, right? You scale out. So Amazon bought more servers, but guess what happens after the vacation is gone? You're basically just sitting on top of servers that you're not using. And then came the brilliant idea, if we're not using them, let's rent them. And so this is how Amazon Web Services was actually born. They were one of the first to do this. And then everybody followed. So you have Google Cloud, Azure, and so on. So plenty of new providers that appeared. But this is the idea of providing resources to everybody. And a concept here is called the elasticity of the cloud. If you are a user of a service like this, then you can just press buttons and then create machines and then stop the machines when you don't need them. It's extremely elastic, as opposed to buying your machines and physically storing them in your basement, right? So 20 years ago, cloud was a buzzword. It was just like blockchain or, it was really that buzzy. All right, now it faded away a little bit, still there. So what is now a specific technology of Amazon is called S3, which means, if I correctly remember, simple storage service, right? S3. It's basically what we discussed, storing objects, billions of objects with a simple key value model. S3 does exactly this. So the way they do this, is based on an abstraction, but it's really just an abstraction called a bucket. So buckets are like containers for your objects. And users of Amazon S3 can create buckets. A bucket is identified by a bucket ID. Everything I'm telling you is on the logical level, right, for S3. So it's a bucket ID. And if you zoom in on just one bucket and you look inside, there are objects in there. Object, again, is just a name for file, right? But we like to call them objects here. All right, it's a sequence of bits, more precisely. So if you have a bucket ID plus an object ID, that is your key, right? It's a compound key with the bucket ID and object ID, but that together is your key. And with the key, you can access and put or get an object from S3. That illustrates latency, because now I have high latency with my clicker button. So there is a max size that you can have on S3, which is documented as of 5 terabytes. That's the maximum size. It's plenty of room for one Star Trek episode, but there is this limit, right? And we will see how we break that limit actually later on, but this is it. So you can put and get objects, maximum size 5 terabytes. The number of buckets, in order to prevent abuse, is 100 per user max, and you need to ask them via a support ticket if you need more than 100, right? So you create your buckets. The reason is that the names are unique worldwide. So if everybody creates too many buckets, at some point it starts to be crowded, right? So this is why we have the limit. And now I'm going to take some time to talk about all these scary numbers with a lot of nines. When you are a company, you have customers, you have a contract with your customers, and you promise them things. This is why you have an army of lawyers in order to draft these contracts. And in these contracts, we have that kind of numbers. This is durability. There's other kinds of them, but durability is what's the probability that your object is still there in a year. You put it in there, will you see it next year? Well, there is a probability of 99.999999999%. And that actually means that every year they lose 1 out of 100 billion objects, right? So it's like a lottery. Every year there is 100 billion objects, one of them just disappears, right? That's the guarantee, but they guarantee you it's not more than that. Not more than that. Then it's up to you to deal with that. What will you do? Maybe you store it twice, right? And then I will let you compute the probability of losing the 2 of them, but that's how you do it. But you need this sort of guarantee for your customers, because again, who are your customers? It's going to be Netflix, it's going to be, all of these companies that provide services. So what happens if the object that loses the resolution of the cliffhanger of your favorite episode just disappears, right? You have a problem. So this is why we have these guarantees. And typically it's with a lot of nines. I'm waiting for the next slide to appear. Yeah. There is another kind of guarantees with lots of nines, that is the availability. Because maybe the objects are still there, it's not lost, but maybe the system is down and you try to get an object or put an object, but you just get some error, right? That the system is momentarily down. So in the contracts, you might have a guarantee that says it could be down 0.01% of the time. So it's up 99.99% of the time. This is 1 hour per year. So this is lots of nines. And this is how things work. Waiting for the next slide, please. No, doesn't want? Yes, the next slide. So I just write, so you have the orders of magnitudes, right? This is basically how you determine. 99% is like 4 days. That's rather a lot. If you have 5 zeros after the period, it's like 4 seconds a year, which is pretty strong. That's availability. It's not loss, right? Because then it's back online and you don't lose anything. Yet another example of plenty of nines is the response time. How quickly do you get an answer if you have a get or a put? Now, if you think of it naively, you might think, okay, let's just guarantee an average response time, right? But it's not really viable. You cannot really do that. Instead, what you reason with is percentiles. You basically promise, let's say, that we guarantee you a response time below 10 milliseconds 99.9% of the time. And maybe 1 in 1,000 times, you will have more than 10 milliseconds, right? But the rest of the time, we guarantee you the 10 milliseconds. That's another kind of guarantee you get. Okay, that was the legal part. It's called service level agreements, this sort of documents. All right? Do we have a question over there? Yeah.
So my question is, like, when it comes to the service level agreement, two of those things, like the downtime and the response, you can easily measure that yourself. But say they lose my 2 documents, and I suspect that their loss is a lot lower than they say it is. Sorry, their loss is a lot higher than they say it is. How could I go about getting my money back or taking Amazon to court?
This is the lawyer thing.
Okay.
So basically, it's really all about law, because technically the engineers are designing the system in such a way that it provides these guarantees. What happens if it breaks? Then the customer can sue and the legal team will take care of it, right? But the job of the engineers is to try to make sure that this is actually enforced.
But how could I verify it?
How can I
verify?
Verify?
Because I have no visibility over.
Well, maybe you have your own legal team as a customer, and then you ask engineers to investigate it. I think it's really about bringing in front of a court of law, proof that it wasn't fulfilled. But I think when it comes to that, it means there was an escalation, right? So typically there are several. I mean, it's not a law lecture right here, but still it's interesting to know. So what typically happens is that you first talk with each other, right? When that happens, then there is something called arbitrage, where you have some mediator with whom you can speak, and there have clauses in the contract that say you first go to arbitrage, and only then can you go to a court of law. You can even forbid going in front of a court of law, right? But this is really beyond the technical aspects of things, right? This is really legal stuff. Yeah. And I'm not an expert in law. I mean, I'm just telling you from my experience, but yeah. Did I still partially at least answer your question?
Yeah.
Okay, awesome. All right. I'm going to tell you about something that is exciting. That is one of the discoveries that were made along with big data. You might remember this ACID thing, right? With the guarantees of transactions and so on, the consistency. And then we met the real world, where things are actually not that simple. And the conclusion, it's a very famous theorem. I'm unsure why it's called a theorem, because it's more of a conjecture, but it's known as the CAP theorem. It's yet another one of these impossibility triangles. You cannot have the 3 of these at the same time. So you have to kick one out. And different systems make different choices. So let me explain why you cannot have at the same time atomic consistency, availability, and partition tolerance. First, I need to define them. Consistency here is atomic consistency. It's not the same thing as the consistency I told you about in ACID. That's something different. You have here a system, because you scaled out, that might have 100 or 1,000 machines. Obviously, one of the benefits of having 1,000 machines is that when you have millions of people connected to your system, you spread them over the machines, right? Not everybody is talking with the same machine. So that's called the load balancer when you redirect them to the machines. Atomic consistency means it doesn't matter who you're speaking with, which nodes you're speaking with, you will get the same answer, no matter which node you are communicating with. This is a very strong requirement called atomic consistency. All nodes will give you the same data. The second one is availability. It means that the system is available. It's the same 99.9 blah, blah, blah % about the downtime of the system, right? So your system is available at all times. And the third one is partition tolerance, for which somehow I don't have a slide, but the idea is easy. There was a natural catastrophe that basically disconnected the America from EMEA, right? So everything is broken and there is no communication anymore. And you're out of luck because half of your nodes were in the US and half of your nodes were in Europe, let's say. This is called the network partition, right? You can no longer have the entire set of nodes communicate with each other. Partition tolerance means that if that happens, of course, that's an exaggeration, right? In practice, it might not be like as strong as that, but this happens. Partition tolerance means that if that happens, that doesn't break the system. You can continue to operate. You might need to wait until the partition is resolved, but it's not going to crash. It's not going to stop working. You will just, for example, become unavailable during the partition. So this is called partition tolerance. And the reason you cannot have all three is illustrated by this. Imagine that I have a system where everything is consistent and all the nodes see the same things. Then I make an update. In order to make an update, I'm going to be communicating with one node, just one, right? So imagine it's this one, and I update something here. So at that point, this node right here has a newer version of the data. Everybody else has an older version. How do I achieve ideally consistency? If I want a consistent system, I need to propagate my update fast enough before anybody else accesses it, right? So I need to propagate the update to the rest of the network, right? If I do it fast enough, then they will all again be consistent. But what happens if there is a network partition right there, and now I have half of my nodes on the left, half on the right, then I couldn't propagate the updates. So now you see that in that case, either you say, okay, it's not available, you just stop serving your customers until it reconnects, or, because that's a choice, or you say, okay, I continue to be available, but I have to accept that people in the US will have this newer version, and people in Europe will have this other version, right? The older version. So it's either or. Either you stop serving your customers and ask them to wait until this is resolved, or you continue to serve your customers, but they will not all see the same data, right? Of course, there is a third alternative because it's a triangle. The third alternative is that if this happens, everything just crashes and that's over, right? That's the third alternative. Right, so this is the CAP theorem, and there are systems that are CA, others that are AP, and others that are CP, right? It's all these three possibilities that I told you. Is there a question over there? Careful with the seating, small hops, yeah. It's like in start, yeah. Go ahead.
I'm wondering, in practice, is it the case that there's usually one node connected to all the other nodes to have fast updates?
Oh, you're talking about the topology of the network.
Yeah, just the network you draw before. Yeah.
So you could have a centralized network, right? We will see that actually in the next weeks. We are going to have these sort of things when there is a central node. But then you are not you cannot be all three anyway. This is totally orthogonal to the topology. Yeah. But if you have a central node, then you will probably become unavailable if there is a network partition. So you don't have the three options, then either you crash or you become unavailable. Mm-hmm. But then it's not an option to just be not consistent because you have this one node that you need for the system to work, right?
Yes.
It just removes one option.
Okay. Thanks.
Right? All right. So, yeah, maybe we can take 1 minute. Go ahead. Yes, but then there's a network partition that might disconnect this, right? But if that's a peer-to-peer network, basically, what you describe. Yeah. The CAP theorem would also apply to this, to the peer-to-peer network, right? Okay, who understood everything? 80%? More than 50%? Less than 50? Okay, that sounds about right. So thank you very much. I'll see you tomorrow for the continuation of this. Sure. Have a nice evening. Goodbye.